Okay, we're moving on now to our second part of chapter 4, okay, which is some additional work we're going to be doing with random variables. We looked at a binomial probability condition and distribution in our last slideshow. Here we're going to be looking at some other types of random variables. Okay. Normal random variables are a very important concept in statistics. There's a lot of basis on the idea of what is normal and what is a normal distribution throughout our statistical assumptions. Okay, so let's look at some types of random variables we're going to be dealing with here. We know we can, especially if they're numeric, we can either have discrete or continuous. Okay, a discrete random variable is a random variable whose positive values are distinct, separate numbers on a number line, such as integers. When we were counting number of heads in a coin flip, that was a discrete random variable. Okay, a continuous random variable is a random variable whose positive values lie in an interval of real numbers. So just if you want to kind of put that out of the math language and into general terms, discrete random variables count things and continuous variables are usually measuring things. Okay, binomial random variables, which is the slideshow we just looked at, were one example of a discrete random variable. We counted the number of heads, the number of times we rolled 6, blah, 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 blah. We're going now to look at the continuous random variable. Okay, that's going to be our next type of random variable that we dive a little deeper on. Okay, so what are some examples of continuous random variables? The amount of sugar in a randomly chosen orange. Okay, the range of that amount of sugar can be anywhere from 0 on up to infinity. Okay, the height of a random student at GC. The range of that height can be anywhere from 0 to infinity. The grade of a random student in Math 111 based on a percentage. Any range for that grade from 0 up to 100. Okay. Recall this sketch of a symmetric unimodal distribution, which we call bell-shaped. If you remember back when we did our density plots and we described them, okay, we're looking here at a bell-shaped curve, unimodal and symmetric. Now, when the distribution is roughly bell-shaped, which is what we're looking at here, okay, about 68% of the values are within 1 standard deviation of the mean, 95% are within 2 standard deviations of the mean, and 99.7% are within 3 standard deviations of the mean. Okay, so now what does that mean? Let's look at this thing first. First of all, what are we doing here? Anytime we're using a bell-shaped curve or a bell-shaped distribution to talk about probability, okay, or percent distributions, it's important to remember that we think of all of this area underneath the curve as representing 1 or 100% of all of the outcomes. If you remember a density plot, we should see the majority of the outcomes at the peak of the plot, okay, and very few of the outcomes out at the ends of the plot. So position inside or under this bell-shaped curve is going to determine probability based on the fact that this cell is all area set equal to 1. Okay, so let's look at this. If you were to create an RStudio density plot of heights of UC Davis students by gender, okay, so we have here response explanatory, okay, data equals UC Davis 1. We have a title, and we have the layout of the plots. Okay. We also can look at the mean and the standard deviation. Again, that should come from Favstats. Both variables here, we can see that. We have the females with a mean of 64.4 and a standard deviation of about 2.51, and the males with a mean of 69.59 and a standard deviation of about 3.5. Okay. Now, We know that female heights distribution is bell-shaped. Okay, how do I know that? If I look back here, it is fairly symmetric and bell-shaped. Okay, so I expect it's going to have a mean, because I know I calculated my fave stats, mean of 64.5, standard deviation of 2.5. Assuming that these females are representative of the entire population, okay, about 68% of all females at UC Davis have heights between 62 and 67 inches. Okay, now how did I calculate that? Mean minus the standard deviation, mean plus the standard deviation. Okay, so we're concentrating. Look at this. If I split it down the middle, that's where the mean is supposed to represent. So if I expand a little to the left and a little to the right, and I'm thinking about shading in all this area here in the middle, okay, I am modeling the percentage of respondents who should be between this range, okay, and it's about 68%. Now, what would happen as I continue to shade outward? If I were to continue to shade outward, I would cover up a higher and higher percentage of the area under the curve, thus representing a higher and higher percentage of the respondents in a particular group. Okay, so if we want to expand that range out further, we want to get it to include more people, 95% of people, we're going to subtract 2 standard deviations, which would be 5, 94.5 minus 5, and then we're going to add 2 standard deviations. So now we have a range of 59.5, 69.5 inches. If I want to expand it out a little bit further to get practically everybody, I'm going to subtract 3 standard deviations or add 3 standard deviations. Okay. Can you make the same claims for males? So if you're watching this right now via video, you need to stop this video. You need to go back to the slideshow, and you need to look and see if you can do this for males. Okay. So many bell-shaped distributions are called normal distribution, and this is what like the idea perfect normal distribution would look like. Okay, perfectly symmetric. We have nice balance and symmetry there. The distribution for a normal random variable, any normal random variable x, we call this a normal curve. It's going to be bell-shaped, and it's going to be symmetric about the mean, and that mean is going to be the expected value. Okay, it also has spread, standard deviation of x, which we will see called sigma. Okay, mu and sigma, mean and standard deviation. Okay, and then once we know that we have a normal distribution, that it is bell-shaped, that it is symmetric about the mean, then we know this 65-95 rule applies. Okay, so here's the thing. When we're observing scores or we are looking at any particular measurement in a normal distribution, we want to have an idea if a score is unusual or not. We might calculate a z-score to validate that. Okay, now how do we do that and what does it mean? First of all, we're going to take whatever measurement we're trying to decide, if it's bigger or smaller or just normal, okay? We are going to take that value, subtract the mean, and divide it by the standard deviation. Now, what are you really doing here? You're really trying to find out how many standard deviations, whatever value you're observing is, away from the mean. Now, we know that can be positive or it can be negative. If it's negative, that means this value is smaller than the mean. If it's positive, this value is greater than the mean. Okay? Anytime we are beyond 2 standard deviations away from the mean, either larger or smaller, this is what we would say unusually large or unusually small. Okay, here's an example calculation of that. Suppose the mean number of hours on social media each week for college students is 20 hours with a standard deviation of 4 hours. Okay, now first of all, what do we know that means? 68% of students in this population are going to be on social media between 16 and 24 hours. Mean minus standard deviation, mean plus. 95% of these students would be on social media between 12 and 28 hours, okay, minus 2 standard deviations plus 2 standard deviations. And 99.7% of this population would be on social media between 8 and 32 hours, minus 3 standard deviations plus 3 standard deviations. So let's look at the Z-score of a student who spends 30 hours on social media each week. Okay, what is that student's Z-score? So we take the result we're interested in, that's this student, we subtract the mean, we get an answer of 10, and then we divide that by the standard deviation, which is 4. So we get a Z of 2.5, okay? Now, because this is beyond 2, we know this is unusually large. Could it have been negative 2.5? Yes, and that would still count as unusually large. It would just be unusually small instead of unusually big in terms of this measurement, okay? Since this student's score is 2.5 standard deviations above the mean, we know that they spend more hours on social media each week than some of their peers do, okay? That's an unusually high value. So now let's take this again. This is a practice problem. You need to stop the video and see if you can calculate it yourself. Find the Z-score for a student who spends 16 hours a week on social media. Is this an unusual value? Find the Z-score for someone who spends 7 hours each week on social media. Is this unusual? Okay, we'll have a video for these as well. All right, so here's basically what this 68, 95 rule for probability means, okay? If we have a roughly normal distribution, the probability of any result for the random variable falls within 1 standard deviation is about 0.68 or 68%, okay? So if I take the random variable that's supposedly centered on the mean, hopefully, okay, and I subtract a standard deviation and I add a standard deviation, I should get 68% of all the results in that range. Okay, 95% when I subtract 2 and add 2 standard deviations, and 99.7 when I subtract 3 standard deviations and add 3 standard deviations. Okay, an example. Suppose the number of hours college students spend on social media each week follows a normal distribution with mu equals 20 hours and sigma equals 4 hours. Let X, random variable, represent the number of hours on social media by a college student. About 95% of college students spend between what two numbers of hours on social media each week? So 95%, 2 standard deviations, okay? So that would be 20 minus 2 times 4, which is 8. So that would be 12. And 20 plus 2 times 4, which would be 28, okay? So we see the work happening down here. So the probability that we randomly select a student who spends between 12 and 28 hours on social media is 95%. Okay. When you can't use the 68-95 rule, that's where we're going to bring in RStudio to help us out. Okay. This is a command called pnormgc. It is going to take a specific result for us, okay, in whatever scenario we're working with, and given the mean and the standard deviation, it's going to tell us how likely we are to get that result and whatever comparison measurement we're using. In this case, if we want to know the probability of randomly selecting a student who spends more than 18.5 hours on social media, the format for that would be the command pnormgc, okay, the boundary, the region we're using above, because we're greater than, okay, and we have a mean of 20 and a standard deviation of 4. Yes, we want to see a graph. It's not going to look like the graphs we're used to. When we saw binomials, these were bars, okay? Again, that's because those were discrete. These are continuous. We see our 18.5 hours marked off, And just like we think, it's slightly below the mean, it's off center. But we wanted the probability of choosing a student who spends this time or greater. So all of these results in the shaded area would count. In this case, 0.642 as a probability, 64.62% chance. Okay, what about less than? This is the probability of randomly selecting a student who spends less than 15 hours on social media. There's my boundary. The region is below because we want less than. Mean is 20, standard deviation is 4. We want the graph. Marks off 15 and goes below. So we have about 11% or 0.1056. Okay. Now in between, we've seen these before. We've seen these in binomials, no different. The probability of choosing a random student who spends between 15 and 22 hours on social media. Okay, what's different here? The boundaries. Just like with binomial, when we created a in-between scenario, we have to list those in list form in RStudio. So the letter C in parentheses, lower bound, upper bound. Region is between, mean is the same, and standard deviation is the same. And we will see that the command shades between the two. Okay. Now here in this case, we can have an outside scenario. This prompt might read the probability of choosing a student who spends less than 17 hours or more than 27 hours on social media. We can bring in the outside region. We're still going to have a list. We're still going to have C, lower bound, upper bound. But instead of between, like we had here, we're going to have outside here because we want less than 17 and we want more than 27. And on the graph, we see this is an outside shading, okay? Less than 17, more than 27, 0.2667 probability, okay? When a random variable is continuous, okay, the probability that the random variable is less than that random variable, okay, is equal to that probability is pretty much 0, okay? Now, let's think about that for a second. Consider our normal random variable. To get the probability of x equaling 23, being exactly 23, we would compute this between 23 and 23, okay? Now, that would give us 0, okay? We're thinking about this as the probability of being where we expect it to be continuous, okay? So if you ever want to run that command, it's R is going to produce 0 here, okay? Now, let's say that suppose we want to know the number of hours that creates sort of a boundary for us in a different way, okay? We want to know the number of hours that whoever the student is spent on social media weekly by a student who logs more hours than 80% of all the other students, okay? So what are we looking for here? We're looking for the length of time on social media that this student would have to spend, okay, that would put them in the 80th percentile, okay? Remember we said percentiles were rankings. So we want to know where the cutoff is. Where's the cutoff for 80%? Okay, this is called the 80th percentile, and there is a command on RStudio that will do that for us. It's called qnormgc, okay? Notice that the input format here, the percentile, the region, the mean, the standard deviation, the graph. Now, why is the region below? Most of us are dealing with percentile here. We are looking at the 80th percentile, so it has to be, this number for hours has to be greater than or the same as 80% of all of the other measurements. Okay, so that's why we're using below. Remember, we talked about if you were ranked, we put everybody in order. It would be the 80th person in line. So we're using below. That's due to the definition of percentile. Okay, so if we run that qnorm command, it's going to shade in 80%, okay, from kind of the middle out to the bottom and then go from the bottom up here. Okay, because we wanted the 80th percentile. We didn't want the middle 80%. So we have 23.37. That's the number of hours that somebody would have to spend on social media in order to be in the 80th percentile. Okay. So here's another example. Find the number of hours for a student such that 75% of college students spend more time on social media than that student. Okay. Now, here's when we end up in a situation about changing from below to above. Now, let's think about this. This is not the 75th percentile, folks. We said 75% of students would be above this. And that's technically the 25th percentile. Okay. And we could do this command as 0.25 and we would do below. Okay. However, here we've put in 0.75 and we've set the region to color above. So it's going to shade that 75 and show you what the boundary is between the upper 75 and the lower 25, which is exactly what we're looking at here, 17.3 hours. Okay. The question wasn't phrased in a way that we could use the term percentile. How could we change the wording so that it was? That is exactly what we just talked about on the previous slide.